How's it going, guys? In this video we're going to keep going with the thermochemistry series, and this time we're going to cover Hess's Law. But real quick, I just wanted to go over something really quick. In thermochemistry there's 4 different common ways to calculate delta H. We have calorimetry, which we did in the last video, Hess's Law, which we're about to do, enthalpies of formation we'll do in the next video, and then bond enthalpies we'll do in the video after that. And yeah, this is just, it's good to know how to do it in each of the different ways. I think you can have multi-part questions, or you never know which one you're going to get asked, so it's good to go over them all. So now we're just going to jump in here to thermochemistry, Hess's Law. So what is Hess's Law? Regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. So it sounds kind of weird and wordy and abstract, but we're going to kind of just put that aside for now. We'll jump into the first problem and then we can kind of make sense of it. Okay, so calculate the delta H for the reaction A yields 6C. And usually with these problems we're given like 3 or sometimes more, you might even get less than that though, reactions. And basically this is just telling us what we know. I like to think of it as like these are other reactions that were done maybe in the same lab and they measured them. And the delta H of each of these was calculated. And so for the first one there, A yields 3B, that was 30 kilojoules resulting. The next one is going to be 60 kilojoules, and the third is going to be 20 kilojoules. Basically what we're going to do, the reason I like Hess's Law problems, it's the most like a puzzle out of like any type of thermochemistry problem, I think. Basically we're just trying to figure out how to make this out of these using basic algebra. So first of all, what I like to do is think of this as a multi-step problem. We know here A equals 3B and 3B equals 6C. 6C we can see is our end product here, and A is our reactant. So here we go. We can just set it up like this. A yields 3B yields 6C. And basically, you can see A eventually yields 6C. Again, I'm not using elements for this. It seems kind of weird, but you can get problems set up like this without elements, and you can kind of just do it the exact same way that you would otherwise. Right here, so we'll just review this. Regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. So the sum of this change and this change, essentially. So what we have here, we know is 30 kilojoules. And here, when we go from 3B to 6C, we have 60 kilojoules. So we're just simply going to add them. 90 kilojoules, and we've just calculated the delta H for A yields 6C. And now a lot of times you're going to get the follow-up question, is this exothermic or endothermic? We can just really quick reference this. Delta H, if it's greater than 0, it's endo. If it's less than 0, it's exo. And there we go. We have 90 and it's positive, so that's going to be endothermic. So that's probably one of the easiest types of problems that you can get in Hess's Law. So now we'll do a more like commonly challenging one. Given H2 plus F2 yields HF2, sorry, 2HF negative 662.4. They're usually going to be, at least in my experience, not clean numbers like up here. Just to kind of increase the odds that you make a calculation error somewhere along the way. CF4 This one's going to be, we'll say, negative 980.1 kilojoules. And then we'll have 2C plus 2H2 yields C2H4, and the delta H on that is going to be 32.5 kilojoule. And it can be like that. Sometimes it seems almost totally random the way that the equations are. And then the question is going to be calculate delta H for C2H4 plus 6F2 yields 2CF4 plus 4HF. So right off the bat, that's a much trickier question that we have. And I'm using pen for the sake of it being more visible on camera, but I would always recommend using pencil for this, just because it's kind of like, you know, there's a lot of different ways you can do guess and check work to kind of figure out what you want to do. I like to just put my delta H up there, kilojoules, and then just start going through. So in basically, again, just like we did in the first problem, we're going to try to make the final equation out of these equation fragments, and then whatever we do to these, we do to these. So if we double this, we double this. If we switch the arrow of this, for instance, like CF4 is going to yield C plus 2F2, we're going to reverse the sign, so we're going to make that a positive 980. And that's basically all you need to know. And then it's just getting more and more skilled at knowing which combinations add up the quickest. And these are, you know, if you're not practiced well enough, these are something that can really take up a lot of time on a test. And if it's a multiple choice question that's worth the same as everything else, it's like, you know, you don't want to lose time to answer another one accurately because you're hung up on answering this one. So we'll start off with that. C2H4 plus, you know, yields 2C plus 2H2. That's going to equal negative 32.5. What we did here is wait, hang on. So what we did was, whoops, that's should be C2H4. We reversed this equation here, so we got negative 32.5, and now we have that, the C2H4 on the reactant side. Now we're going to try to get our 6F2, and we'll see where that comes from. So in this case, there's a few different ways we could do it. We could do 6 times this equation, multiply this by 6. We could do, you know, half and half on different ways. This is a 6F2, so it looks to me that what we might want to do is, if we multiply this by 6, you can kind of think a couple steps ahead. We're going to have to multiply this whole thing by 3 to get 6F2, and then you're going to have 3 C's. Do you really need 3 C's? You're not gonna. It doesn't look like we have any C's alone. So I think what would be a smart next step would be, in this case, to do 2C plus 4F2 yields 2CF4. And then in this case, we just multiplied this by 2, so it's 980.1 times 2. And we're going to get negative 1960.2. So here we have, and that's, I'm sorry, so that's 2, that would be 4F2. So we're part of the way there, but what we also did was we secured our 2CF4 on the product side. So now we'll keep going. What about the 4HF? We'll see what we can get there. To get the 4HF, we'll see what we have. Where do we have HF? We have 2HF here. So here's how we're going to get the other 2F2. So sorry if I'm kind of going through this in a kind of a random order. That's just, I guess, the way my mind works. But we're going to take this 2F2. We have 2 more F2s that we need. So we can just kind of go in through the 2 H2 plus 2F2 is going to yield 4, because we're multiplying everything by 2, HF. So now we got our 4HF on the product side. We got the 2CF4 on the product side. We got our 4F2, 2F2, and then our C2H4 from our first one. So here that's going to be negative 1324.8. And now we can just kind of, what I like to do is get everything I need and then just hope that things cancel out. And maybe that's not the best strategy, but it seems to usually work, and I think that a lot of times the problems are intended that way. Maybe it's just the types of problems that I happen to be doing most of the time, but I have 2C plus 4F2 plus 2H2. And I like to just go straight like from top to bottom and not try to rearrange them, because again, that's another way I found that I sometimes will make an error. For HF. Okay, so now we'll just simplify this down. We have 2 C's over here, 2 C's over here. Now we have 2H2 over here, 2H2 over here. And later on we'll kind of, I don't know, basically in chemistry you could almost think of these as intermediates, and you're ruling them out because they're superfluous in a way. They're on both sides. We have our C2H4 plus 4F2, which is what we need. I'm sorry, that would be 6, because we have 4 plus 2. Yields are 2CF4 plus 4HF. So obviously we'll consolidate that. This is going to be 6. And there we go. We figured it out. And now we just have to get the sum, because Hess's law is the sum of all changes. And these are the changes that we chose to do. So I'll just do that calculation. We're just summing these three, and those are going to equal, we get negative 3317.5 kilojoules. That's our final answer, and we can also add that that is going to be exothermic, just in case they ask. Cool. Hopefully I don't run out of room here. I'm going to go on to question number 3, and we'll just say okay, given okay. And you don't always need to, I think that a lot of times the states of matter aren't completely relevant. There's probably a few cases where they will be, but in this case I'll just write them for like the sake of it seeming like a real reaction. And then for our delta H, we'll have negative 174.5 kilojoules. We'll have negative 298.3 kilojoules. And then we'll have negative 42.6 kilojoules. So, like I like to think of it in my head, the last 3 scientists, or the last 3 experiments that were done in your lab, all were exothermic, and these were them. Now we're trying to basically use those reactions to calculate the delta H for this. CS2 plus 3 O2. It's going to yield CO2 gas plus 2 SO2 gas. Okay, so let's see what we can do with that. Now, like I said, what I like to do is just kind of go through it in order from left to right. CS2, where do I see CS2? Right here. The easiest way and the only way to get the CS2 on the reactant side is just to reverse this equation, giving us 42.6. So we'll have that to start. CS2 yields C plus 2S, and the delta H is going to be, like I said, 42.6 kilojoules. And if you think you're liable to forget what the sign is, then you can always put like a positive there. I tend not to, just because, you know, it doesn't seem necessary. Now the next thing, 3O2. Where do we see an O2? There's two places. There's O2 here, there's an O2 here. So this is one of those times where it's probably worthwhile to think ahead. What are we getting on the other side? If we get 3O2 here, we're going to get 3 CO2. How many CO2 do we need? Just one. So the other option is we can get, so we need 3O2 here. We can do we could do 3O2 here. Then we'll get 3S, 3O2, and 3SO2. But we only need 2 SO2. So I think what it seems like the most bang for our buck would be to assume that we'll find the other O2 through the next step and just kind of go for what we can solve, the 2S2, and get pretty close to the O2. So what we're going to do next is C plus O2 yields CO2. And that's going to be negative 298.3 kilojoules. We're actually going to stick to 1 for now. We're just going to do exactly what was given. And then we're going to have, for our next one, so first of all, we can kind of think back in our head. Where are we at right now? We have CS2 plus C, which we don't need, plus O2, which we need 2 more of, yields C, which we'll cancel because we have it here and here, the 2S, which we don't need and we actually need to get rid of, and then we have a CO2. So we have as many CO2 as we need. We have as many CS2. Let's see how we can figure out about getting the rest of our O2 and our SO2 all in one step. That's going to be multiplying our first by 2. So 2S plus 2O2 yields 2SO4, which is right here. I'm sorry, that's SO2, which is exactly what we need. And then our delta H for that is going to be 2 times 174.5. And we're going to get negative 349.0 kilojoules. All right, cool. So we're closing in on this. Now we just make the sum. So we have CS2 plus C plus O2 plus 2S plus, there's a few ways to do it. You can do it out this way, which I guess I already started, so I probably should finish it. 2O2, or you can simply use these equations and look at them and compare them, which will save you about a minute. And you know, if you're well practiced on it, it shouldn't be very risky to just do it that way. If you didn't study as much as you feel you should have or something, or you're a little rusty on these problems, I would just write it out this way. I think it's the most tried and true for me, but I'll grab this and see what we can cancel out. So we need this, we need this, we need this, and we need these. Let's see if we can get rid of everything else. C, 2S, 2S. Perfect. So now we know we're going to end up with exactly what we need. And that's just going to be the sum of these 3 things here. So 42.6. And we will get delta H equals negative 604.7 kilojoules. And this is going to be exothermic because it's negative. Alright, we'll just do one more. It's probably getting to be a pretty long video here. But you can always skip around or pause and do one and then see how you feel. C2H2 plus. This is going to be a tricky one, comparatively. Or it's at least going to have the illusion of being tricky. Now we're going to have C plus O2 yields CO2, and that will be negative 204.6 kilojoules. And then lastly we'll have H2 plus 1/2 of O2 yields H2O. And delta H is going to be negative 332.8 kilojoules. Okay, so we're down to the last problem, and the weirdest thing about it is that there's some fractions there in the mole ratios. Shouldn't be a problem though. Let's just forge ahead. Calculate delta H for 2C plus H2 yields C2H2. So thankfully there's no fractions in this final answer, so we're not going to have to do anything too crazy for the math. First off, let's just ignore them and start with what is most straightforward. We need 2C, and there's 1C here, and you know, we can figure out the getting rid of the other ones for now a little bit later if we need to. Let's just start with the 2C. And I think a lot of times these can be really overwhelming if you're not someone that enjoys puzzles or whatever, math puzzles, algebra puzzles, whatever they are. They can seem pretty overwhelming initially. I think though the best thing to do is just to start and just to start throwing numbers down, equations, even if it's just, you know, exactly what's here. If it gets you closer to the final equation that they're looking for, just start, and the more you do it, the better you'll get at finding shortcuts and skipping ahead. So in this case, we'll have the we'll just multiply it by 2, pretty straightforward. The next thing that we're going to do is we have the 2C taken care of. We have other things we don't need though. Now we'll just go down H2. We have H2 as the second thing. We'll just throw in exactly what's there. 1/2 O2 yields H2O. We don't have to do any calculations. We know that the delta H is just going to be 332.8 kilojoules. Now let's just kind of check back in mentally where we at. So we have our 2C, good. We have our H2, good. We have 2.5 O2, which we don't need. We have 2CO, which we don't need. We have H2O, which again we don't need. We have a ton of stuff that we don't want. So what's the best thing to do here? And usually these can all be done in 3 steps. I mean, sometimes it takes more than that if it's a really complicated question. This is one though that we only need to do 3 steps. There's one more step, and this is probably a good time to pause and try to figure out what it is, the last step that you use to balance this out and to get the resulting formula. So what we're going to do is we're going to take this and reverse it. So we're going to have 2CO2 plus H2O. It's going to yield C2H2 plus 5/2O2. And that's going to be a positive 1840.2. We're just going to reverse the sign on that. So here we go. We have 5 halves, and now we're just going to do some really basic, I think back to algebra basically. see what we have too much, or see what we don't need. So this we're hoping not to cancel. This we're hoping not to cancel. And then the only other thing we have here is this we're hoping not to cancel. So ideally, that's how you can eliminate everything that's not circled. We're hoping to cross out. We have 2 O2 here, a half an O2 here, and yeah, so we have 2.5 O2. However, 2 over 2 is 1, and we have, so basically if you had to do 2 O2 in terms of halves, you would have, so you'd basically have 4 O2, 4 halves. So yeah, sorry. 4 over 2, and this is 5 over 2. So 4 plus 1 equals 5. Simply put, we can add this, add this. We're consolidating our O2s into 1 and then canceling them all out. So now we don't have to worry about O2. Let's see what else we got. We got 2CO2, 2CO2, H2O, H2O. Not bad. So now we're just going to end up with the 2C plus H2 yields C2H2. And then we're going to, as we know in Hess's law, we need to sum these. So the enthalpy change for the reaction is the sum of all changes. So we're going to take this, this, and this. And honestly, like I said, the better you get at these, the fewer steps that you're going to need to do, and that will save you in the end from more calculation errors. Because you can imagine if we had, 7 different steps here, and we're putting 7 different numbers into the calculator, we have a much greater chance at making some kind of a clerical error along the way. So we're going to end up with, that's going to be 1098.2 kilojoules, and it's positive, so that's going to be endothermic. So that was, I think, a pretty thorough overview of these Hess's Law problems. If you're pretty confident on them already, maybe you only need to do 1 or 2 of these. But yeah, they're here if they help.